Thank you very much. And now Pablo is going to be very practical for us, talking about Bayes.
Thank you, Cal. Very good. Welcome, everybody. This was a fantastic introduction by Dr. Jens. I cannot call you that, by Frederick. It was awesome. I am very happy and enjoyed it. Thank you so much for the presentation. We're going to try to go practical now that we also know that Bayes was a amicable fellow. So for this talk, I will aim to talk between 30-40 minute stops. So if I'm reaching the edge of that, somebody can throw something at me and I will just stop and you can throw things. You're in throwing distance of mandarins. Yeah. But the idea is we're going to go to talk a bit about the uncertainty quantification and its role in nuclear physics. I'm going to actually give a 3-minute introduction to nuclear physics in general for physics friends that are non-nuclear, for nuclear physics friends that just want an introduction, and for everybody else that is neither physics or nuclear. And then we're going to go through a different perspective, resonance, but from maybe a different angle on how to apply Bayes' theorem. We're going to go through a practical example that is a Jupyter notebook that you all have access to through the GitHub repository. And then we're going to describe the hands-on challenges, and you will take it from there. So throughout this presentation, please ask questions. I really enjoy when the discussions are discussions. And as I said, if we're running out of time, I will just jump to the very important part, which is you playing with the hands-on sessions. So nuclear physics for Smarties in 3 minutes. I made this before making the introduction, and then I realized it's going to take like 5 minutes. So we'll have to make a second edition of the book. This is an atom, and most likely you have heard of atoms in general. They are composed by a nucleus and electrons that are flying around. And from different types of atoms, you can make the chemical periodic table that is seen here, original idea by Mendeleev and some friends. Now, in nuclear physics, we don't have space for the electrons most of the time, so I'm going to strip my atom out of all these electrons, if only experimentally that was so simple, but I'm a theorist, so I can do that. And I'm just going to focus on the neutrons and the protons, and I'm going to call this the nucleus. And if you put all the nuclei together that you can make, you get the nuclear periodic table. And this looks slightly different than the chemical periodic table. And one of the main differences is that now we can talk about neutrons. I can say, for example, this particular nucleus is carbon-12, 6 protons, 6 neutrons, the thing that basically makes everything that life is made out of. So everyone that you love is highly percentage, a bunch of carbon atoms put together. And if you zoom in the carbon region that is sitting in here, you can see that my carbon-12 is sitting as one of the stable isotopes of carbon. And I have many other flavors that I could be. I could start adding more neutrons to carbon. I could start removing some neutrons for carbon. Frederick was talking about calcium-60, that is way up there, and he's adding a bunch of neutrons to the calcium isotopes. And the important part that I want to highlight in here is that at EFRIC, we are called the Facility for Rare Isotope Beams. We're mostly interested on the ones that are really rare, that are very hard to produce, are very unstable. We want to study those properties and try to get a hold of what the heck is happening. This is a very busy slide, and I just want you to look at it. I'm going to guide you to some parts, but this is the thoughts that I was able to put on a Sunday afternoon of what we do in nuclear physics. We're going to be talking throughout the summer school a lot about binding energy. That is going to be kind of like our writing course example of things. Imagine that my analogy is that you have protons as oranges and neutrons as apples, and if you weight how much weight has every orange and every apple, you get some numbers. But if you put them all in a bag, apparently you find out that the bag of 10 apples and 10 oranges doesn't weigh as much as 10 times the number of apples plus 10 times the number of oranges. There is some missing weight that in this case is we call the binding energy, and that is the energy stored in the glue that makes the nucleus stick together. So we're going to be talking about binding energy interchangeable with the term mass throughout the school. In EFRIC, we're interested, and in nuclear physics in general, we're interested about many things that nuclei do. For example, I might be interested in understanding how neutron stars merge together to create elements and form many of the isotopes that we see on Earth. I might be interested in doing nuclear reactions, and there's a lot of things that can happen in there. Your nuclei can just bounce and go on their separate ways. One of them might be captured by the other, they might break. It's a lot of things that can, a zoo of possibilities. I might be interested in particular decades that will tell me something fundamental about the laws of the universe. And nuclear structure in general, this is a funny comment that I once heard somebody said that nuclei are like ogres because ogres are like onions, if you have seen Shrek. So nuclei are like onions as well because they're usually layered in shapes, not just a bag of things, but they have orbits. So we're interested in all of this. Now, the reason why this is really hard, all of this is really, really hard. And the reason, in my mind, is twofold. The first one is because the rules of the game that we're playing are unclear. Imagine that we don't totally understand how a proton and a neutron, just by themselves, interact. We have a lot of models and approximations, but the rules themselves are not super clear. So you can imagine as if we were playing a game of chess, and we're trying to infer what exactly are the rules. Nobody told us. So you can do this by watching people playing, but the challenge increases because you can only watch one instant at a time, and it's actually dark, and half of the screen doesn't work because neutrons are really hard to make them interact with anything. And also you're wearing sunglasses. So this is how doing nuclear physics looks like. So this is the first challenge. The second challenge is that even if you were to learn perfectly well what are all the rules, you have an increasing complexity. When you have a proton and a neutron, maybe two, you are like super amazing and predicting everything they're going to do. You put a lot of those together and you have the rising complexity. And I put as an example the game of life. If you haven't seen this, I recommend to you, it's amazing. You can watch videos and a lot of discussion about it. This is a game of some sorts that have very simple rules on how cells are alive or dead in a board. And the thing is that from those simple rules, amazing complexity arises, like this thing that just moves throughout the entire board, shooting out a bunch of particles. This is coming just for these particular rules. Turns out that this is Turing complete, so actually you can code in the game of life. That's how complex this ends up being. So, having said all that, it's a wonder that any of this works, given these two challenges. And that's why we need to quantify our uncertainties. We need to make sure that whenever we're predicting things, whenever we're measuring things, we take into account these two problems so that when we say to somebody, hey, this is how you should be a nuclear reactor for energy, things work out as they should. I'm not the only person saying this. There is a list of very smart and very knowledgeable people that agree that uncertainty quantification is important. My example is here is from the long-range meeting that happened last year. And in there were a lot of presentations. Many of them were highlighting the importance of Bayesian statistics, uncertainty quantification, and this type of interdisciplinary approaches. So we have come to the right place at the right time because we all need to know what uncertainty quantification is about. Okay, that was my 3 minutes introduction to UQ in nuclear physics. Now that I have convinced you that this is important, and I think we convinced you before because you traveled here, how will you do it in the context of nuclear physics? You have some theory friend and some experimental friends. You put them together. The experimental friends, she was able to measure all these things. Your theory friend was able to come up with a model. And my model, I'm going to use a notation that is some model F that depends on parameters alpha. That is this red curve. And I'm trying to explain the data through this model. What I want is to be able to obtain some uncertainty bands using, or some credible intervals using the technology that Frederick mentioned. We're going to do that through Bayesian statistics. This is for posterior distribution for alpha given y. And I'm going to go into the details of that in a second. But this works out in a simplification way in 2 principles. Everything is a random variable. And we're going to put assumptions on how they interact. And what we want to do is to model how they propagate and how they basically play with each other. So the 2 advantages, which by the way, I have been working on Bayesian statistics since my PhD. I'm super excited about all of its applications. This condensation of how this works came from very good discussions with Edgar. The 2 advantages of this method is that first, you're putting your assumptions in a very clear way, so everybody can go and criticize and say, hey, we can improve this way you model your uncertainties. And it allows for a natural continuous learning. The posterior of today is going to be the prior of tomorrow. Okay, I said it correct. So whatever we learn today is going from our posterior analysis is going to be what comes in your prior for the next analysis that we'll do. So a procedure, which is what we're interested in, is compromise between our likelihood or prior and the evidence that Frederick was talking about. And here is the simplification of what I think. What I think when I see this. This is what I want. This is what we think happened. A way to explain how the data came to be. The prior is what we think we know or what we believe. And the evidence at the end will tell you more or less how everything that you're doing makes sense, depending on its value. By the way, I have a picture of Thomas Bay here, and this is not a picture of Thomas Bay's, most likely. As Frederick pointed out in many discussions, we don't know a lot of the details from that time. And most likely this is a picture of an uncle or somebody else that is assigned to be based, but this is the picture that everybody uses when they're talking about this. Okay, let's go to an example of how this will be constructed. For example, I could have a prior of my alpha. On Frederick's example, he was having e to the minus beta squared over sigma beta, and he was assuming his prior was Gaussian or bell-shaped with a center 0. In this case, I might assume that it doesn't have a center 0, but it's centered somewhere else. I might actually say, you know what, physically, I know that my quantity alpha can only be positive. So I'm going to use a truncated prior, a truncated Gaussian. I'm going to say that any value that is negative cannot be. And that is a fairly reasonable assumption that you can make. For the likelihood, I might be tempted to say, well, you know, all these points look, I'm going to think that the errors came out as Gaussians, and I'm going to model this, as many physicists usually do, as my e to the minus chi-square, my chi-square being the definition of the residuals. And we're going to have a nice discussion later on why this is not necessarily the great notation, because this is a notation for a variable that is distributed in a chi-square distribution. And usually when you're talking like this to statisticians, they will look at you weird. So part of what we need to do in here is to establish good bridges and connection and to make sure that what we're saying is actually correct. But that will be a way of modeling your likelihood, saying, I think my errors are Gaussians. I think my model actually describes my data, and I'm going to assume that they're distributed in this particular way. Now, once you put all those things together, you arrive at what is usually the discussions that we as physicists have with our statistician colleagues. For example, we might be trying to measure the scattering of neutrons in a nucleon of calcium. So our statistician friend, this is a cartoonish representation of Frederick. He has a farm, and usually he has birds on his hat whenever we're talking. So that's why it's a cartoon. So the first questions will be, what is the previous knowledge? Well, you know, as a prior, we know that the nuclear radius of calcium should be around 3 femtometers, 3 point something. And how much around? Well, I don't know, maybe between 2.8 and 3.30. Okay, we're going to use some skew distributions for the prior, because you believe that it's more skewed to the right than to the left. A next question will be, how was the data taken? And the experimental friend, she says, we had 2 detectors. One was very precise for my quantity x smaller than 2, and the other one was not very precise for x bigger than 2. Actually, the value at x equals 2.3, the person that was taking the shift at that time got distracted playing Zelda, so we don't believe that data very well. So we're going to probably need to model that with something else. Okay, so the statistician friend says we're going to use a likelihood model for each, and we're going to check the sensitivity of our results to that value at 2.3, and things change a lot, and it looks like an outlier. I'm just going to drop it, and we're not going to tell anybody, because yeah, Zelda is an amazing game. That's okay. Other questions might be, are we going to deal with any other models besides F? And your theory friend says, no, F is the only model. No, wait a minute. As third character appears, another theory friend that says they have developed their own model that actually is way better at explaining them. And as you go on, they start discussing and arguing, no, because your model doesn't explain this part, this one doesn't explain that part. And it's like, okay, don't worry about it. We're going to mix their models, respecting their domains of expertise. So we're going to do some model mix. And then the question will be how long it takes to evaluate each model for a given parameter alpha. And model 1 takes between 2 to 3 hours per alpha, and model 2 takes around a second. We are in deep trouble if any of those things are true, because then whenever we need to do our Monte Carlo sampling to estimate posteriors, it's going to take years or decades or years or minutes to finish. So the answer there is that we're going to need emulators. And then you have some computer and math friends. These are cartoonish representations of Edgar and Kyle. They're like, yay, emulators, let's go and build some very fast. After you have done all of that, the goal is that we get something like this, in where I have my two models with their uncertainty bands. If everything worked correctly, they're mixed in some way, where we were taking both models at the same time. And I have a posterior distribution for my parameters, alpha 1 and alpha 2, that I can then use to extrapolate predicted quantities, just look at the graph and feel very happy about myself. And that is how the story ends, except when we say, okay, but we really need to make sure that you're mixing the models in an appropriate way. Otherwise, you might be able to arrive at wrong conclusions that depend on a specific model. And Alexander is going to talk about that in the afternoon after lunch. Okay, let's go to a practical example. Imagine that I give you some data with 95% errors, whatever the heck that means. Some of the time, you might be facing the situation where you read a paper, all of the people that made the paper are dead, you have nobody to ask, and you're like, well, I'm going to assume that this is what they meant when they put that error back. But if you can talk with the experimentalist, that is usually better, because you can get a better modeling of this. So these are the things that we're going to try to get. Imagine that I'm making a model that is linear, my coefficients alpha. So the first thing that I want to build for my posterior is the prior, what we think we know. And I might come and say, for previous knowledge, or just at least looking at the picture, I can imagine that my intercept alpha 0 is around 0, and my slope is around 2. Yeah, wait. Okay, so I'm going to choose a Gaussian, because those are easy to then combine with similar likelihood. So I'm going to choose a Gaussian for my prior, and this is a notation that statisticians use. When I started learning about these things, I hated this notation. Now I love it. It's perfect. You say, like, this is distributed as a normal distribution with mean mu and variance sigma squared. So we're going to model that way. And you can read about multivariate normal distributions. The generalization of many dimensions from the regular Gaussian is straightforward. Here's a Wikipedia article that is usually a place that I like a lot to go and check some things that I do not know. And in the Jupyter Notebook example that is on the GitHub repository, you have all the definitions and everything that I use to make these examples. So you can go there and check how these functions are built. Also, we have our prior. Now let's try to create our likelihood. I like to think of the likelihood of what we think happened, how this data came to be. And I'm aware that I'm going to be mixing a bit, Bayesian notations and frequentist notation, but to me, it has helped me go through many of the derivations and things and to understand things there. So the way that I think about this doesn't have to be the way that you decide to think. Is that I have my red point that is my data at my location xj, and I'm going to say, you know what, my model is really good. So I'm going to assume that my data was actually exactly on top of the model for some given value of a true parameter. But if, and that model is this purple curve. But since there are errors that might be coming from my model, might be coming from the experimental person that was playing Zelda, I'm going to say that I need to add some noise there, some error to something that is going to move this point away from that perfect value that I could have recorded. And that's what I call these epsilon j's. And I'm going to assume that they're distributed with mean 0. We are not biased in that sense. That is an assumption. And with some variance sigma j. So then what happened is that my data was on my model and it was corrupted by this fact. That's how at least I like to think. And if you were to describe these things in a frequentist approach, you can think that you could have a histogram that is centered at your perfect model. And every time that you run the experiment, you just get different values of these noise.
So does the choice of modeling the noise with the Gaussian distribution matter? So if
100%. Yeah. So if these were counts, most likely a better distribution would be a Poisson distribution. And that's the key. Most of the time, and that's why I want to have this whole discussion. Let me go back in here. That's a fantastic question. Thank you. Most people that not most people, a lot of people that I have encountered that do physics and statistics, they think that this is what you need to do. Every time that you have your likelihood, oh, that's easy, e to the minus chi-square, the sum of the residuals, and you're done. It's like, and if your errors are not Gaussian, and what if other things need to be taken into account? That's why I want to take a pause, not think in terms of a recipe, but you're sitting there and you're trying to think how the data that I'm seeing came to be into the world, taking into account the model that I have. So if my things are counts, I'm going to use a Poisson distribution. If the thing is more complicated, I'm going to use something more complicated. Most likely, I will have no idea what to do, and then I need to ask statistician friends to tell me. Make sense? Fantastic. Any questions? Any more comments? Thank you for that. Very good. So, how the data came to be. So, if I focus on that particular point, I'm going to say that the probability distribution of observing that yj, right, that is the likelihood. The likelihood is given the model, what is the chance of observing this particular value of my data? I am going to model it as a Gaussian because I'm assuming that my noise is Gaussian and that my true observations are centered at this value of my model. So this is the probability distribution for that. And now if I want to say what is the total probability distribution of all my observations, and if they are independent, if that is a very important if, I can just multiply their probabilities. And because of exponentials being the way that they are, you arrive at the fact that this is e to the sum of the square of the residuals. And that's what usually people use as the e to the minus chi-square. Now, since many things tend to Gaussians, as you start adding independent stuff together, this is sometimes not a bad assumption, but it's not what I want to get across is that this shouldn't be the place to go automatically. We need to think if this is a good idea to do whenever we're modeling the things that we model. This is the definition in terms of the code, if you want to check out the likelihood distribution. And after you have done this, what we want is to sample from my posterior. This is the probability distribution of alpha given my data, and I want to make these nice plots. How do we do that? Well, one way of doing it is doing the GIF sample, or if you know your distributions exactly, in this case, this is a linear model. I'm assuming that I know the noise, so actually we just sample directly from the Gaussian. But let's pretend we don't, just in case your model was more complicated. And I'm going to guide you through relatively quickly through the Metropolis algorithm. It's 5 very easy to follow steps. The first part is you start somewhere. So you propose a starting location on your parameters. These are parameter 1 and parameter 2. The next is I'm going to propose from where
that red star is an indication of planet Earth on the Milky Way.
Yes, exactly. How do you know? Yeah, actually, it looks very much like that. So I started in planet Earth, and I'm going to propose to go to a different planet. That is done at random. I could just say sample a random Gaussian direction around my point. And then I'm going to compute the ratio. This is how the Metropolis algorithm works. The ratio between my likelihood at parameter, the new parameter, divided by the likelihood at the parameter that I was. I obtain a number. In this case, let's assume that is 0.8. This is telling me, the fact that this number is less than 1 is telling me that for whatever I'm doing, parameter 1 is a bit more likely than parameter 2, because the likelihood is a bigger number, because I'm doing the ratio of these two things.
These are posterior, right?
No, these are likelihoods. And they should be posteriors. You're right.
No, they are posterior.
They are posteriors. They're posteriors. Thank you, Fred. Yeah, you're right. Thank you so much. So the next step is I need to pick a random number between 0 and 1. And this should be an S, not a T. Let's suppose that the random number that I draw between 0 and 1, in this case, is 0.4. The next step is that if this number is bigger than this number, I should move to my new place. And if it's lower, I should stay. So my question, mental gymnastics, so we don't fall asleep. What should I do in this particular case? Should I move to the new location according to Metropolis, or should I stay where I was? Move. I should move because this number is bigger than this number so the ratio between the two is bigger than the number that I got. This T should be an S. So I should move to my new parameter. And you can think intuitively, this means that if, for example, the posterior value in my new location is bigger than where I am, I should move no matter what. That is already a more likely situation that I want to go. And that's why the random number, I'm showing it between 0 and 1. So you repeat this 100,000 times, because locally in this case, everything is very fast and we can compute stuff. This is a Metropolis algorithm that you will have and you can play with. And once you do that, you get your posteriors. Go ahead, Frederick.
Oh, but yeah, go back one slide. Just want to make sure that so we use in Metropolis Hastings algorithm, we use the notion of rejection. And so when you're moving, you're not rejecting.
Yes.
So I think that's why maybe some people intuition would have backwards, because I think when you move, it means you accept what it is that you're given. So you move.
Yep. And if I don't move, then I stay wherever I am, and I add that to the back of places that I have visited. Basically, this is going to be doing a random walk around my place and trying to explore how my posterior looks. Okay.
Question: what happens if R is greater than 1? Then you accept no matter what?
You accept no matter what. And yeah. And
that's what you said.
Yep. And the paper that Metropolis was credited for, but Metropolis was not credited for, proves why this is equivalent to sampling directly from your posterior. Fantastic. Now, suppose that I want to calculate new things. I have already my posterior plot, what we like to call the corner plot, that involves my two variables. And I want to say, what is the probability distribution of obtaining some new observation in here? That's usually what we want to do in the clearance. I do my model, some data, and now I want to see what is the prediction on the other side. Well, you're going to grab all your visited parameters. You have a long list of 100,000, which, by the way, some might be repeated. I might have the same parameter twice, because at some point I proposed somewhere to go, and then the method decided to stay, and that's fine. I want those repetitions, because that is telling me that region is somehow important to the explanation of the data that I want to do. So you grab all these 100,000 points. You grab your m values from the list. In this example, I'm grabbing the first one. You go and calculate what is the value of your prediction, your function f for that values of the parameter at that location. In this case, I'm saying that it's around 5.8 for this particular value of the parameter, and you make a histogram of all those things. And then you put that histogram in there, and that's it. That is your central prediction. You will have a mean value that you can report as the mean, or the median, depending on which flavor you want to do, and it will have some standard deviation or sense of credible interval that you can also report as your error in this case. And that's it. High five, we have done it. I can have my prediction for my model on the new locations that I'm seeing, and this is how the uncertainty bands is going to look like. Now, important thing, you see that these bands or credible intervals are not just straight lines. And the reason why they're not straight lines is because I am not just finding the minimum value of my maximum value for posterior, finding some interval in my parameters and just plotting the two lines that I get from that. This is a collection of 100,000 lines that I got from my posteriors all put together. And at each location, what I do is I truncate between obtaining 95% of my entire distribution. I truncate the 2.5 of the lowest part and the 2.5% of the biggest part. These are very important distinctions. In here, I'm plotting the credible interval for my model F, for my model prediction. If I want to plot what an experiment might see, I need to take into account the epsilon. So the thing that I want to get across is that these distributions for the purple and the orange are not the same. The purple is showing the posterior distribution for your model, where you believe your model is predicting things. The orange one is predicting where a new experiment might come from. So even though I am pretty certain that my model lays in here, in this particular X, I know for a fact that if somebody goes and measures there, the measurements might not lie exactly in there because I have these fluctuations. Somebody might play, I don't know, celda 3, and then the thing will fluctuate up or down. So that is an important thing to take into account. And in the notebook that you can use as inspiration for the other challenges, you will see this code available and you can use it. And that is it. And I made it in half an hour or less. I'm super happy. We can go now to the hands-on sessions. Before you jump and start doing everything, I'm going to go through all the challenges that you can do. And you can choose your first battle, choose your team around you. You can work in teams or work alone. And all the organizers are going to be flying around helping folks. And Kyle is going to at some point explain how the code space works. But before, let me discuss the challenges. These are the 1, 2, 3, 4, 5, 6, 7 challenges that you can take for today. And by the way, if you don't finish, that is completely fine. You can finish later, or this could be part of the project that you want to tackle for the final outcome of the semester. So I added an arbitrary difficulty star. Don't trust me too much on this. This is what I think. But it might be that you pick one of the first ones that has a lower difficulty, and it turns out that it was one of the hardest. The first one is Frederick's derivation, given that he didn't go through the completing the squares or dealing in this particular part, in this particular example with the inverse gamma distribution. You can play with that. You can try to convince yourself that what he was saying was correct. And you can ask him for generalizations. What will happen if you try to now derive an expression for both? How should that look like? The second challenge is a spectrum from data challenge. I am borrowing this from a project that I was doing with some experimental friends and theory friends here at EFRIC. Basically, it is that you have observed some data counts from a detector, and you believe that the process that generated these comes from a bright Wigner distribution, basically a number of peaks, resonances in your system. This was done for the decay of oxygen 26 to oxygen 24 and 2 neutrons. So every time that these things breaks and the 2 neutrons come flying out and the nucleus itself comes flying out, this is telling you what are the probability distribution of the energy of the particles that come out of that process. So I want to, from these data, that you're only going to have access to the red data in red, recover what was the spectrum that came from that with proper uncertainty quantification. So this is going to be the second challenge. The third challenge is the convergence of Monte Carlo. As you saw in my slides, my posteriors look gorgeous because I'm doing 100,000 samples on my metropolis. That takes like a minute or less in these very fast computers. But what if your model takes 2 hours or even minutes? Maybe you don't want to do 100,000. Maybe you only have budget for 1,000. This is how the posterior is going to look in that case. What the challenge in here is for you to get familiar with what is the price that I pay in terms of my accuracy of any predictions that I try to do by the fact that I have finite number of computers. And this is going to make tomorrow's session much more appreciable because of all the shortcuts that we're going to teach you on how to take such that you can increase this time, this sampling. The third,
Can we add another piece to this challenge?
but of course,
Anybody who likes geography? Anybody like geography? Yeah. Figure out what place in the world looks like the picture on the lower left. There's one place in the world that looks like that picture there. Figure it out.
very good. I'm literally going to put that into the GitHub, and that is a bonus challenge, the bonus part of this challenge. We need an answer later. So we have an answer. Okay, the third part is estimating the noise level. Now, Fred. So here's a kind of a historical personal perspective. For a long time, I don't want to say how long. For a long time, I thought that in statistics we always knew for errors. That was an assumption. Of course, I have sigmas, and I'm doing e to the minus chi-squared. I know what the sigmas are. My experimental friends in all their wisdoms measure that. What have you done? What if I give you these data points and you have no idea what were the uncertainties associated with this? If I were to tell you, I think these points came from a linear process between y and x, let's walk this through intuitively. If I tell you that, does it make sense to assume that the experimental errors in my detectors were 25? Like, will you believe that these folks measured these points at this exact location plus minus 25? This is not a rhetorical question. I want a strong answer. No, right? Because if the fluctuations were of the size 25, all these points should be all over the place. Will you believe, if the model of linear response is correct, that the errors were 10 to the minus 3? Not as well. That makes no sense. Where between 10 to the minus 3 and 25 should be the noise? Well, that is for you to estimate. That is what this is going to guide you through. And it's using the exact same ideas that, by the way, for a statistician, this is the first thing that they teach them, how to handle the noise level. So that's why it's important to talk with them, because they already know how to solve many of these problems. Go for it, make your Monte Carlo sampling. And now you're going to also be sampling for the noise itself. So you need to be sampling on both. Frederick.
I see you have Frederick's variations in the corner. Thank you for putting that in.
But of course.
Yeah.
Yeah.
And for this particular one, it's so the challenges that I have in the 2 slides that we went through with the math. The first one is you have to complete a square. The second one, which is in this slide deck, you have to just read and make sure you agree. That actually answers this question as well. It's the same question.
Yeah, exactly. Interesting. These corner plots or correlation plots, you're going to find that the noise level might have some correlation with your model parameters, which means they're not independent. Depending on the noise level that actually happened, you might conclude one thing or the other with your parameters. And that is crucial, because then that means that your physical conclusions out of this depend on what level of precision these things were measured. The next challenge is the liquid repol. I am stealing this completely from BTEC's class in nuclear structure last semester. So those of you that took this, if you want a re-challenge, you can go for it, but you probably have done already this. We didn't do it in a complete Bayesian way, so this can even be a nice addition to your knowledge. The liquid drop is explaining masses of binding energies of our nuclei, and it's a model that has 4 terms in this particular case. So your job is to grab the data from nuclear masses that is on the GitHub and try to make a fit or a model calibration and get some plots on the posterior values for the parameters. The next challenge is a model selection challenge. I just put this because I really like it. You're going to work with the data from the electron scattering. I don't know if you have heard of the proton pulsar. That is something that I work on some time ago. The main idea is I have some data that looks like this, and I'm trying to estimate the slope at 0, because the slope at 0 relates to the proton size. What you're going to do is play to see how, using data that you know, because you're going to generate the data, how a straight line or a parabola make the fit to the model. And what you're going to find is that the line has a very small variance, but is biased because the data is curved. So the line cannot capture that curve. The parabola, on the other hand, is unbiased, but has a huge variance because it's more sensitive to the noise structure in the data. And this is the final challenge. I'm putting 3 stars on this one as well. Is for you to go and play. I have no idea how to do this. I have never done this. So if you do it, you can teach me. But I have found a web page that has very clear animations and some sort of explanation. That's why this has 3 stars. Go and play with different sampling techniques. There is a lot of research going on, and that has been already, on how we can make these things more efficient. In this particular part, I'm plotting the Monte Carlo, the Hamiltonian Monte Carlo. Go and try to compare with Metropolis convergence questions. Can I get a better posterior distribution and estimation of parameters with fewer samples? That is a very important question to answer. And if not, the other thing that you can do is look at the clear animations because they're reports. That is all that I have. Thank you so much for listening. And Frederick has a question.
No, just a comment on what you wrote. So I don't know if you guys can see the fine print, but this is going to be available, right? You can go back.
This is on the GitHub.
Yeah, it's already there. Yeah. So Hamiltonian Monte Carlo is it's kind of like one generation beyond the ordinary Metropolis Hastings, and it's existed for some time. But recently, I think it's in 2016, there's a version of Hamiltonian Monte Carlo called the no U-turn sampler, and so a lot of folks are using no U-turn sampler now. It's not really, more complicated to use. It's not more computation demanding. It just seems to work better in a lot of cases. So, I mean, this is maybe something you can find out for yourself by doing this challenge.
And final thing before I forget, thank you so much, Frederick. I'm going to upload this to the Google Drive that I already posted on the Ascension forum, so you can have access to the slides as you go through, and Frederick's slides are already there. That is it. Thank you for listening, and let's go to the challenges. Sorry?
You need some mark for the code spaces.
Please, Kyle is going to explain how code spaces works. Give me just 1 second to upload this in here. Oh, it's already there. Okay, it's already there. Then go for it. And wow. So we're going to go in here. Okay, 1 second. Let me. Go for it. It's hard because I'll figure it out.
All right, so just a brief remark on how we're going to use these code spaces. If you go to the Ascension GitHub page, which is just github.com/ASCSN, it's going to be pinned on that page, so you'll be able to click it. You can also type in this long string if you're really feeling like it. Also follow the GitHub page while you're there. Like and subscribe. Thank you very much. Once you're here, you're going to want to fork this repository, because there may be issues if you try to run the code space directly from this, because I'm not paying for it. And that does mean that whenever we have different hands-on sessions, if you have some irresponsible organizers like me who is still going to add stuff tonight, then you'll need to make sure you pull in the changes tomorrow, but we'll walk you through this. No worries. It'll be easy, hopefully. So what you'll do once you fork this repository into your own GitHub account is click the little code button and then click plus to create a code space on the main branch of the repository. Pablo already has one here, but we're gonna make a new one. And what this is going to do is create a virtual machine somewhere on Azure's cloud, and it's going to give you a VS Code work environment and a full Linux terminal. You can do whatever you want here. There's no way you can break anything for everybody else. So be destructive if you really want to. But if you want to be constructive, you'll find the various files here or various folders for the different sessions. And in fact, Pablo has put in, very exciting.
Wow.
Pablo has put in.
That sound of implosion under the sea.
Yeah, perhaps. It's a little delayed. So this is Pablo's first code space experience.
Mm-hmm.
And I recommend you go ahead and click this because whenever you start trying to run things, just like a standard Jupyter notebook, it's going to ask you to set up some environment things. Just blindly click yes, install, install, install. It won't install to your computer. It'll install to this instance. And then you just run everything like normal. So just again, install, 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 install. I trust all of this.
Yes, of course, we trust Python.
Yes.
Well, Freddy doesn't trust Python.
Don't like snakes.
And the next realizations are going to go smoother because everybody will have their own code space.
Yeah. Oh, it's thinking.
It's thinking.
Woo! Excellent. Ah, wow. There we go. There's Pablo's first code space experience. If you can't get this pretty plot of how many users there's going to be in the code space as a function of time, which I don't know if we're going to hit these metrics, let us know and we'll come around and help you with the technical problems. But other than that, Pablo might have some things to say. The practical base folder is where you're going to want to be, and I hand it back.
Thank you. And as a very illiterate person in Python and in software, it's okay to say, I have no idea what I'm doing and I don't even understand what Cal was saying. And we will go and help you. If you know, then fantastic, and you can help your friends around. And thank you so much. I want to give a round of applause to Cal because this was made by him. The fact that we can run all these things in there, he by himself built Microsoft so that we can run. Yes, so thank you. Okay, we're good. Go for it. Break stuff.
We'll write on my yacht later.
The yacht that is on top of the yacht.
Yes.
Thank you so much for the timing. That was perfect.
Yes.
Yeah, that's that.
What?
Yeah.
So you invented Linux, huh?
Yeah, I invented Linux. I invented Windows. Actually, it was a dark time in my life.
So that was back when you at Xerox in the late 60s.
Yeah. I was friends with
So folks, I'm going to stop sharing the screen and I'm going to stop the recording as well. I will leave such that the recording is safe and then I will join back in and you can ask questions. Good luck with the challenge.